On September 28, 1969, just before 11 in the morning, a fireball tore across the sky above southeastern Australia. It split into 3 pieces over the town of Murchison, and one of those pieces struck the ground hard enough to leave a small crater in a farmer's paddock. When locals reached the rock, it was still warm. It smelled of methylated spirits, and it was older than the planet they were standing on. That single stone, weighing about 100 kilograms in its scattered fragments, would become one of the most studied objects in the history of science. Because when chemists in Melbourne and at NASA's Ames Research Centre began to crack it open, they did not find dead mineral. They found amino acids, dozens of them, glycine, alanine, glutamic acid, the exact molecules that, when chained together in long strings, become the proteins that build every living thing you have ever seen, touched, eaten, or been. And then they found amino acids that have no counterpart in any organism on Earth. Molecules that life on this planet does not use, has never used, and yet were sitting there inside a rock that had spent the last 4.5 billion years drifting between worlds. That is the part nobody quite knew what to do with. The Murchison meteorite was not contaminated by Earth. It was carrying a chemistry older than Earth itself. What you are about to hear is a story that scientists spent 50 years refusing to take seriously, and then, one experiment at a time, were forced to reconsider. It is the story of how the building blocks of life were found everywhere we looked in the cosmos, except where they were supposed to be. And by the end, you may find that the question is no longer how life began on Earth. The question is whether it began here at all. To understand why that question is so destabilizing, you have to understand how recently we believed something completely different. For most of the 20th century, the standard picture of life's origin was simple and parochial. Earth formed about 4.5 billion years ago. It cooled, oceans condensed. Lightning struck a warm pond full of simple chemicals, and through some patient miracle of chemistry, those chemicals organized themselves into the first replicating molecule. From that molecule, all life, every redwood, every whale, every neuron firing in your skull right now, descended from a single chemical accident in a single puddle on a single planet. The universe was the stage. Earth was the only theater. There was a problem with this picture, and the problem was time. Imagine you are watching a film of Earth's first billion years on fast forward. The planet finishes forming about 4.5 billion years ago. For the next several hundred million years, it is hell. The surface is molten. Asteroids the size of cities are smashing into it constantly, in what geologists call the late heavy bombardment. The oceans, when they finally form, are repeatedly vaporized by impacts. The first moment Earth becomes even theoretically habitable is somewhere around 4 billion years ago. And the oldest confirmed traces of life, found in rocks in Greenland and Western Australia, date to around 3.5 to 3.8 billion years ago. In some interpretations, even earlier. That is not a long time, that is essentially no time at all. Life appears on Earth almost the instant the planet stops being a furnace, as if it was waiting at the door. This is the timeline problem, and it has haunted origin of life research for decades. Because the chemistry required to go from simple molecules to a self-replicating cell is not trivial. It is one of the most difficult chemical transitions we know of, and on Earth it appears to have happened almost overnight in geological terms. Either we got astronomically lucky, or the chemistry did not start here. That is the door Fred Hoyle and Chandra Wickramasinghe walked through. Hoyle was one of the most brilliant astrophysicists of the 20th century. He worked out how the elements heavier than helium are forged inside stars, the calculation that explains where the carbon in your bones comes from. He was also, by the 1970s, considered something of a heretic. Together with Wickramasinghe, he proposed an idea that mainstream biology found embarrassing. They argued that life did not begin on Earth. They argued that the seeds of it, the organic molecules and possibly the microbes themselves, were delivered here by comets. They called it panspermia, an old word with a new urgency. Spores everywhere. Life distributed. For decades, this was a fringe position. The mainstream rolled its eyes, and then the evidence started to arrive. To see how the evidence began to mount, you have to leave Earth. In 2004, the European Space Agency launched a spacecraft called Rosetta. Its target was a comet with a name that sounds like a law firm, 67P Churyumov-Gerasimenko. The mission took 10 years, looping through the inner solar system, gaining and losing speed, threading itself through orbital geometry, until in August of 2014 it caught the comet, a frozen object roughly 4 kilometers across, dark as charcoal, shaped like a rubber duck. Rosetta did not just photograph it. Rosetta flew alongside it for 2 years, riding with the comet as it fell toward the sun, watching it heat up, watching it breathe, and it sniffed the air. On board Rosetta was an instrument called Rosina, a mass spectrometer designed to identify any molecules drifting off the comet's surface. Rosina did something no instrument had ever done before. It directly detected glycine, the simplest amino acid in the cloud of gas surrounding the comet. It detected phosphorus, an element essential to DNA, RNA, and the energy currency of every cell on Earth. It detected hydrogen sulfide, methylamine, ethylamine, a whole pharmacy of prebiotic chemistry drifting off a 4-billion-year-old chunk of ice in the cold dark of space. Imagine you are walking through an empty house, a house you have been told no one has ever lived in, and in one of the rooms you find a kitchen, fully stocked, ingredients sitting on the counter, ready to cook. That is the scientific weight of what Rosetta saw. The ingredients of life are not exclusive to Earth. They are not even rare. They are sitting on the surfaces of comets, the leftovers of the solar system's formation, billions of years older than this planet. And comets, we know, hit Earth constantly, especially during the late heavy bombardment when the early Earth was being pelted by them. Some estimates suggest that the equivalent of every ocean on Earth's surface may have been delivered, at least in part, by cometary impact. If the water came from comets, the chemistry came with it. The ingredients arrived. The question was no longer whether the ingredients of life existed in space. It was now whether life itself could survive the journey. And that question had by then an answer nobody saw coming. It came from an animal so small you need a microscope to see it. The tardigrade is roughly 0.5 millimeter long. It looks like a tiny segmented bear made of pudding. It lives in moss, in seawater, in glaciers. It is, by any reasonable definition, a perfectly ordinary microscopic animal, except that it isn't. In 2007, a European Space Agency experiment called TARDIS, the Tardigrades in Space project, did something that should not have worked. They took live tardigrades, attached them to the outside of a satellite, and exposed them directly to the open vacuum of low Earth orbit. No suit, no capsule, no protection at all. For 10 days, those animals were exposed to the absolute vacuum of space, to temperatures swinging by hundreds of degrees, and to the full unfiltered ultraviolet and cosmic radiation of the sun. When the satellite came home, the tardigrades were still alive. Many of them. They rehydrated. They walked. They reproduced. You have to sit with what that means. Every assumption about what life requires, every textbook definition of a habitable environment, was built on the idea that life is fragile, that it needs warmth and water and protection and atmosphere. The tardigrade experiment broke that assumption. It demonstrated beyond any reasonable doubt that at least some life forms can survive direct exposure to interplanetary space. You might object. You might say a few days of survival is not the same as crossing the gulf between worlds, which takes thousands or millions of years. That is fair. But tardigrades survive by entering a state called cryptobiosis, in which their metabolism essentially stops. There is no clock running inside a dehydrated tardigrade. Specimens revived after 30 years of frozen storage have been documented in the literature. And in 2021, researchers in Japan revived rotifers, microscopic animals, that had been frozen in Siberian permafrost for 24,000 years. 24,000 years, and they swam. This is not one strange result. This is the third independent line of evidence, from the third independent decade, with the third independent set of instruments. Murchison gave us the molecules. Rosetta gave us the chemistry on cometary surfaces. Tardigrade and rotifer experiments gave us survival. Stack them together, and you are no longer looking at coincidence. You are looking at a pattern. Some scientists argue that none of this requires panspermia, that life could still have started on Earth, and these experiments only show it is possible elsewhere. The problem is that the timeline problem does not go away. The problem is that you are still trying to compress one of the most difficult chemical transitions in the universe into a window of a few 100 million years on a planet that was being repeatedly sterilized by impacts. The easy explanation does not actually explain anything. It just hides the difficulty inside an empty word called luck. And then there is Mars. Mars formed around the same time as Earth, but it is smaller, and smaller worlds cool faster. While Earth was still a molten ball of magma being hammered by asteroids, Mars had already cooled. It had a magnetic field. It had a thick atmosphere. It had liquid water on its surface, in lakes and rivers, and possibly oceans, more than 4 billion years ago. Mars, in other words, was habitable before Earth was. There is a window of perhaps several 100 million years during which Mars was a calm, wet, warm world, and Earth was hell. If life is a chemical inevitability given liquid water, organic molecules and stable conditions, then Mars had its shot first. And here is the part that should make the floor feel less solid under you. Earth and Mars exchange rocks. They have done so for billions of years. When a large asteroid hits Mars, it ejects debris with enough velocity to escape Martian gravity. Some of that debris drifts through the inner solar system. Some of it falls to Earth. We have in our museums and laboratories more than 300 confirmed Martian meteorites. We know they are Martian because the gas trapped inside them matches exactly the composition of the Martian atmosphere measured by the Viking landers in 1976 and confirmed by every mission since. These rocks came from Mars. There is no debate. The most famous of them is ALH 84001, a meteorite found in Antarctica in 1984. In 1996, a NASA team led by David McKay published a paper in Science arguing that the rock contained microscopic structures that resembled fossilized bacteria. The interpretation has been contested for nearly 30 years. Some researchers believe the structures are biological. Others insist they are mineral. The debate has never been resolved, but the question is no longer really about ALH 84001. The question is about the mechanism. We know rocks travel between Mars and Earth. We know early Mars was habitable. We know microorganisms can survive vacuum, radiation, and very long timescales. So the chain is complete. If life began on Mars first, and a single Martian rock carrying a single hardy microbe was ejected by an impact, fell through Earth's atmosphere, and landed in a warm sea 4 billion years ago, then every living thing on this planet, including you, is descended from a Martian. This is not science fiction. This is the active research field of astrobiologists at NASA, at the European Space Agency, at universities across the world. It is one of the reasons the Perseverance rover is currently caching samples on the surface of Mars to be returned to Earth, samples that may finally settle the question. Now hold all of this in your mind at once. The Murchison meteorite, full of amino acids that life on Earth does not use. Rosetta, sniffing glycine and phosphorus off the surface of a comet. Tardigrades surviving naked in the vacuum of space. Rotifers, frozen for 24,000 years and waking up to swim. Mars, habitable before Earth, exchanging rocks with us across 4 billion years of cosmic history. Each piece, in isolation, is interesting. Stacked together, they describe a universe in which the chemistry of life is not local. It is everywhere. The ingredients are baked into the dust between stars. The vehicles are comets and asteroids. The passengers, possibly, are microbes that can sleep through eternity. The thing we have spent decades calling abiogenesis, the spontaneous origin of life on Earth, may be a misnomer. It may have been delivery. This is the moment that pays off the question planted at the beginning, whether life began here at all. The most honest scientific answer in 2026 is that we do not know. But the answer is no longer obviously yes. And the weight of evidence, the slow, patient accumulation of independent observations from independent instruments across independent decades, is moving in one direction. It is moving toward a picture in which Earth is not the cradle. Earth is a destination. Take a breath. Watch the slow drift of stars on the screen for a moment. This is the part that does not have a clean ending. Because if life is cosmic rather than local, Every assumption you have ever made about your place in the universe is wrong in a way that is difficult to put into words. The picture you grew up with, the picture every culture on this planet quietly assumes, is that the universe is a vast and lifeless desert, and Earth is the single oasis at the center of it, a miracle of warmth surrounded by infinite cold. That picture is comforting because it makes us special. It makes us the unlikely exception, the cosmic accident worth protecting, the candle in the dark. But the evidence is not pointing at a desert. The evidence is pointing at a sea in which the chemistry of life is dissolved in every cubic kilometer of interstellar space, a sea in which every comet, every asteroid, every grain of dust drifting between worlds is a vessel carrying the ingredients of biology, a sea that has been quietly seeding worlds for billions of years before this one even existed, because the molecules in the Murchison meteorite are older than the Sun. They formed in the cold cloud that the Sun would later condense out of. The carbon in your hands, the nitrogen in your DNA, the phosphorus in the energy your cells are burning right now to keep you alive while this voice reaches you, none of it was made on Earth. All of it was made out there, in the dark, before there was a here. You are not standing on a planet that produced you. You are standing on a planet that received you, and if that is true, then every living thing that has ever existed on Earth, every dinosaur, every fern, every blue whale, every ancestor in your line stretching back to the first single-celled organism in the first ocean, is part of a chain that does not begin here. The chain reaches up, off the surface of this world, through the atmosphere, through the orbit of the Moon, past the orbit of Mars, out through the comets and the asteroid belt, and into the dark spaces between stars where the dust drifts and the chemistry happens slowly, patiently, on timescales we cannot really conceive of. Everything that has ever lived on this planet may be an echo of something that started in the dark between stars. And the strangest part of all of this, the part that should sit with you tonight, is what it implies about the rest of the universe. There are an estimated 200 billion galaxies in the observable universe, each containing on the order of 100 billion stars. If the chemistry of life is cosmic rather than local, if the ingredients are dissolved in the medium itself, then the question is not whether there is other life out there. The question is whether there is anywhere there isn't. The question is whether the same patient sea that washed up onto Earth 4 billion years ago has been washing up onto countless other shores, in countless other oceans, around countless other suns, for as long as the universe has been making heavy elements, which is to say almost as long as there has been a universe at all. We have spent our entire existence as a species looking up at the night sky and wondering if we are alone. We may have been asking the wrong question. The right question, the one the evidence is starting to whisper, is whether there has ever been such a thing as alone at all. Whether the silence we hear is real silence, or whether it is just the sound of a sea so vast that the waves have not yet reached us. You will go to sleep tonight on a planet that you thought was your origin. It may turn out to be your address. The thing you call your body is built out of dust that was forged in stars and assembled in the cold between them, and the life inside that body may be older than the ground it stands on. The boundary you draw between yourself and the cosmos, the boundary between in here and out there, between alive and not, between Earth and everything else, may not be the boundary you thought it was. The universe was not built around us. We were carried into it.